Okay, so today is going to be about principal, or this video, sorry, will be about principal ideals and then irreducibles and primes and things associated with that. So actually, lots of interesting stuff that's important in this one. Uh, just to remind you, so an ideal I subset of R is principal. Just means principal. It's one of those I can't remember. It's PAL or LE. Hopefully, I've got that one right. If and only if I equals to uh, generated by a single element, right? So like that. And just to remind you, this is a little complicated for defining the ideal generated by A in the case where R is not commutative with identity, right? So in general, it was like summation of things of this form. Um, let's say uh, things of the form like W, right? Where W is in, well, let's see, how do I want to say this? Yeah, W would be in, it would be, singleton A, union R times A. So things in R times A, union A times things in R, union things that are have R, something in R multiplied on both sides, not the same thing, but some maybe different thing, right? In R multiplied on both sides, and so it'd be the sum of things like that. And if we had commutativity, we could simplify this a little bit. This W in A union RA, right? And if we had, this is if we have commutative, right? Yeah, commutative. If we have unit, we could simplify this to summation W, W in, I guess we still need all these things. Oh no, we just need things like this. Yeah, so it's just things like that. Because we have a unit, so we can multiply by 1 on both sides, that would give us A. We can multiply by 1 on one side, that would give us RA, 1 on the other side. So anyway, things that look like that. So summation of things that look like that. And then the beautiful one is if we have unit and commutative, then we have the summation of W, where W is in RA, right? But then, right, this thing here just looks like, it would look like, so I'm sorry, a term like this now would just look like R1A plus R2A plus plus like RKA, right? But that is just, the summation. So this would just be the summation of the Ri. So that's just some other R times A, right? So this is actually just RA. And since it's commutative, it would also be just AR, right? So either one of those things. So in the case that so this is with unit, and this is both, right? So if we have both. Okay, and most of the time below, we're going to be interested in the case where we have both. So I'm going to just sort of pretend all throughout here that this thing generated by, an ideal generated by A is just RA, right? Or AR, it doesn't matter which direction I do that in, okay? So just to remind you what a principal ideal is. So that's what a principal ideal is, okay? Let's see, an important thing about principal ideals. So there's lots of important things about principal ideals. Let me do one of the important things first. So if oh, actually no, I don't want to quite say this yet. Oh yeah, okay. So definition, right? So R is a principal ideal domain. Whoops. And this is going to be one of the most important sort of things we look at. And this one gets a name, PID. So we just denote it PID. If and only if every ideal is principal. And in some sense, principal ideal domains you think of kind of being like Z. Okay, so let's see. So first, let's see claim. Z is a principal ideal domain. Oops, I mean Z, the integers, right, is a principal ideal domain. By the way, just to be silly, right? Just to remind you, right? A field can only have two ideals: the trivial ideal 0 and the trivial ideal all of the field, right? There's no in between field. In between ideals in a field. So fields are sort of trivially principal ideal domains for silly reasons, right? So Z is an interesting principal ideal domain that's not an ideal domain for silly reasons. And why is this a principal ideal domain? So let I a subset of Z be an ideal. Good. All right. Then what I'm going to do, so I is a non-empty set, the empty set, right? And we can take, oops, not can't, can take R equal to the min of the set of all, let's say A and I, such that A is greater than 0, right? So we can just do that, okay? So that's a unique thing, right? And why does this exist? Well, this exists basically from the least member principle. And by the way, why are there positive things at all? Because I can multiply by -1, right? Ideals are close near that, so they're, as long as the ideal might just be the 0, right? So then this doesn't happen, right? So it's a non-trivial ideal, right? But if the ideal is not just the 0 ideal, then it does have positive things, and so we can look at the least positive thing in there, and that's the least member principle in Z. And that is, that's basically the same as induction. So it's one of the basic axioms of, arithmetic. So take this thing, right? And then I claim is that I, so remember it's just the smallest positive thing there, is that I is just the thing generated by A, right? So that's what I want to claim, right? So let R be something in I, then R equals, S A plus K, right? For some K, the remainder, right? So, with 0 less than or equal to K, less than A, right? Remember, A is this minimal thing in the ideal, right? Okay, but now what's going on here is I have that R is in the ideal because that's an assumption, right? And SA is in the ideal. So both these things are in the ideal, right? Because, well, multiplying on the left by anything in the ideal keeps us in the ideal, right? But then I have K is equal to R minus SA, right? So that's in the ideal, right? But K is something, it's either 0 or strictly less than A, right? That's an A there. Well, if it can't be strictly less than A, because then it would be in the ideal and it would be positive. I mean, the only way it can be strictly less than A is for it to be 0, right? Otherwise, it would be strictly less than A and greater than 0 and in the ideal, but that violates the way we chose A, right? So that says that this remainder here is 0, right? And so that tells us that R is equal to SA, right? So I took an arbitrary thing in the ideal, and I see that it has the form S times A, and what does that tell me? That tells me I took an arbitrary thing in there, it's in here, right? So I get that containment, that direction, right? Containment in the other direction is trivial because, anything generated in the ideal, I mean, this is the smallest ideal that contains A, and A was in I, right? So these are the same. So in particular, the integers is a principal ideal domain. Okay, so that's an important fact. Okay, let's see. So coming back into this, we want to generalize what I just did with Z, right? And oh, and by the way, I realized that maybe I made a slight mistake just because I don't want to think about things too much. Actually, let me erase that. Oops. Gosh, erase. PID, right? The ID means integral domain, right? So I think I said before that we were looking at rings that were commutative and with unity and had and every ideal was principal, right? But I really want to be talking about integral domains where all the ideals are principal, just so I don't have to worry about any details that I might get wrong otherwise. So I want to like a smaller class of ideals that are going to be really important for us. So so R is a Euclidean domain. Okay, if and only if. So R is a PID. Sorry, R is an integral domain. So that's one condition. And there's what's called a Euclidean function. Euclidean function. E going from R to the natural numbers, okay, such that, and now it's basically looks like the Euclidean algorithm. So for every R and T in R, there exists a Q and R in R, such that S equals QT plus R. Okay, now the Euclidean algorithm had this thing that said that this R would be between 0 and this t here, right? Now that we can't do that here because we don't have any notion. I mean, who knows if we have a notion of order or not. But what we do have here is we have that E of R, right, is less than E of t. So we use this external function to sort of push down on things, right? And we'll use this in the same way we used that fact that the remainder was small in a sense like that, right? And so we'll look at this with a couple of different sort of really interesting examples. And I'll just say, so one of them will be polynomials over fields, and the other one will be the Gaussian integers, right? So the two really interesting examples. Okay, so suppose we have, so that's the definition, right? So we have this kind of funny Euclidean algorithm. There's no requirement that this is unique in this case, right? So I'm not assuming any uniqueness here. And then so here's a let's call it a theorem, I guess. Maybe it's going to call it a fact. Every Euclidean domain is a PID. Okay, and the proof is exactly like what we did before. We're just going to use this function instead of some fact about the remainder. Same proof exactly, right? So remember here we have, so let I be an element, be a subset of R, a proper ideal. It probably doesn't even need to be proper, right? I mean, if it's not a proper ideal, then it's all of R, and so it's just generated by one, right? Which is principal. So let's just say a proper ideal will be in that case, just to avoid any problems. And let R be an element of I with n of R minimal. Right. So in our previous one, I said take the largest positive thing. Take the smallest positive thing, right? I could have let the function e going from z to n be the absolute value, right? Right. So I could have done that, and that would be the Euclidean function in this case, right? But I'm doing the same thing. I'm just taking the element of I and element of I with the minimal value under this Euclidean function, right? Then we have the same argument we had before. So I want to show. Sometimes it helps just to write that so I know what I'm trying to do. R is equal to I, right? That's what I want to show. So let's see. So let same argument, right? So let S be an element of I. Then S equals QR plus. Maybe using R was bad here because I like to use it as the remainder. So I'm gonna replace that with T, right? So I've sort of swapped the R and T around in this one. So I take an arbitrary element of I say let it be in there, right? Then what do we know? Well, we know that E of T is less than E of R in this case, right? Sort of flip those around. And we know that S and QR are elements of I. Now, why is that? Well, S is just taken to be an element of I, and R is an element of I, and so if I multiply R by Q, we stay inside I. That's property of being an ideal, right? And so in particular, T is an element of I, right? Why is that? Well, because it's just S minus QR, right? But E of T is less than E of R, right? And that's a contradiction. Right. Oh, sorry, it's a contradiction unless, we have to be careful here, unless E of T equals 0, right? In other words, unless it's just the fact that we get divisibility, right? So that S equals QR, right? And if S equals QR, well then, we have that S is an element of R. Okay, but yay, that tells me that I, because I took S was an arbitrary thing in here, is contained in R, right? And of course, the other containment's obvious again, right? So I've got that, so they have to be the same, right? So check. Okay, so every Euclidean domain is a PID, so that's a really useful thing. So let's see, what kind of things are Euclidean domains? Now here's where we get, so if we start with a field, and I guess it's interesting to sort of see why we need a field here, then Fx is a Euclidean domain. And we teach this to poor, I don't know, kids in Algebra 2 or college algebra or something. Not quite stated like this, right? But basically we're saying, look, if I can take, how does this work? So the things in here are polynomials, right? So I can take an R of X, so I'll just put the X in there to make it clear, and an S, let's see, to make my notation match, right? Let me take an S of X, sorry, S of X and a T of X, which are polynomials over the field F, right? And so, I don't know what this thing is, so like S of X may be, let's say, a m x to the m plus dot 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 dot, dot plus a naught, right? And T of X, T, okay, I'll drop the X again, right? Maybe Bn x to the n plus dot 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 plus B naught, right? So something like that. So I've got these two polynomials, and I'm claiming I can write S of X equals Q of X times T of X plus some R of X, where I want something to be less, I want something to decrease, and what it's going to be is E of P of X is the degree of P of X. Right, so it's the degree that decreases, right? And so, we teach this in algebra classes, right? When we do polynomial long division, that's what we're doing here, right? And why do you need a field? Well, I have this thing I'm dividing by, which is t, right? So this bn, x to the n plus dot 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 dot, and over here I have this am x to the n plus dot 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 dot, right? Okay, and if the degree of n is less than m, I'm done, right? There's nothing to do. If the degree of n is not less than m, then I need to start trying to divide. So in that case, the degree, so what? So suppose n is less than or equal to m, right? Suppose I'm in that case, right? Then what I can do is I can multiply here by what? It's bn over a. No, sorry, it's yeah. So this is I multiply by an over bn, right? Right. So I hit this thing here. This becomes a. Oh, and then what? X to the m minus n, right? And so this, when I do that multiplication, I get here a n x to the m, right, plus some stuff, whatever the stuff is, right? And you subtract, and you get a lower degree polynomial, right? That just becomes 0, and you get whatever's left, right? And you just keep doing that, right? And so whatever the degree, and when do you have to stop? We have to stop when m is less than n. Sorry, not when m is less than n, but whenever the degree of this thing down here becomes less than n, and that'll be the remainder, right? So there's nothing new here, right? This is stuff you know. Except I'm doing it over an arbitrary field, but all I need to do is I need to divide, right? I mean, that's the point. I need to be able to divide. Now it is kind of useful to think when you can do something like this and you're not in a field, right? I mean, it's because it does kind of come up even in some of your homework. So first of all, let me just say we're done with that, right? So I mean, we have shown that f of x for f of field is a Euclidean domain. Okay, and hence a PID. And so a PID. Okay, so that's nice. One thing you can do dividing in general, right, is if I'm working over, let's see, now you have to be a little bit careful. I mean, let's just stick to uh, integral domains, just so I don't have any sort of real silliness happening. All right, but if I'm dividing by like something that's a monic polynomial, right, so xn plus some stuff, right, b, whatever, let's say a n minus 1, xn minus 1, right, some stuff. And I'm dividing here, into whatever, right? So here it doesn't matter. So b m x to the m plus dot, 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 right? Well, I can always do bm times xm minus n and just hit that thing there because I'm just multiplying bm times 1, right? And so I can do the same sort of argument, right? So even when you're in integral domains, you can divide by monic polynomials, right? Now what you can do in a field is you can make any polynomial monic, right? You can just divide out, right, by the by the leading coefficient, right? You make it monic. I mean, okay, you get some constant times the polynomial, but you're doing the usual sort of things there, right? When you're in an integral domain, there's no reason you should be able to divide out, some such thing, right? I mean, this is even true if you're just over z, for example, and you're looking at zx, right? I can't do anything with 3x squared plus 2x plus 1, right? I can't make this into a monic polynomial of any sense because I can't divide out by 3, right? So this will be important. In particular, this will show up, like we'll see in a bit, that zx is not a principal, so this is not a PID. And that's actually important because z is a PID and zx is not a PID, right? So I had told you before, we'll be interested in cases where R has some property, has property P, implies Rx has property P. It's a pretty general kind of statement, right? But it being a PID is not one of those properties that goes from Z to ZX, right? Or from R to RX in general. Whereas if I have a field, right? So if I have Rx, right? Is a PID, right? Or Z7X, right? Is a PID, or Q of X or something like that, right? Because those are all fields, and I can do division. I can do long division, right? So that's really important here, right? The other example I want to give, which is really nice, which is cool, because it's related to Z so closely, is ZI. And it turns out that ZI, so it kind of looks maybe like ZX, I don't know, but it turns out that this is a PID, and in fact, it's a Euclidean domain, right? So this is, the set of A plus BI. Again, I have a whole set of notes on just this structure, and it's just, I don't know, just a fascinating structure. So, just those things there. And so how does this work? I mean, if we were in Z, we kind of do the division, right, and you get a remainder. And so we want to do something like that, right? But what do we do now? So, I have something in here, A plus BI, and I want to divide by, C plus DI, right? But I can't literally do that. But I can see where I run into trouble, right? So I can try to do this, right? I can say, well, this is going to be A plus BI over C plus DI times, you all know this trick, over C minus DI, right? So I'm multiplying by the conjugate of this guy right here, all right? And so then I get, what do I get? I get A plus DI, A plus BI, C minus DI over, and what I get on the bottom down here is A squared plus D squared. Why do we get a plus D squared in this case? Sorry, C squared plus D squared. I get a plus down here in this case. And notice the only place this causes a problem if I'm trying to divide by 0, but that's something you don't do anyway, right? Well, because when you multiply the I times I, you get I squared, it becomes positive, right? So that happens. And then this up here we can rewrite like this. So we get AC plus BD over C squared plus D squared, and then plus, and then I get AD minus BDI. Sorry, AD minus BCI. Oh, so AD minus BC over C squared plus D squared. I. Okay, like that, right? And what you do, okay, is you just round these to the nearest integer, right? I mean, so there's no reason this is an integer, right? But we can round this to the nearest integer. So we literally just we don't, and here you have to. I mean, there is some stuff to prove. You don't take like the least integer bigger than something. That's kind of what you do when you're doing integer division, right? Is you take, sort of the least integer thing here for that. So we're not literally doing a mod in that sense, but we're doing something like that, right? So here we're taking just, the rounding. I just literally take, round, whoops, this thing here, plus round this thing here, I, right? And so I'm going to call that thing, what do I want to call it? I'm going to call it just, I don't know. Okay, fine. E. What do I want to call it? I'm just going to call it Q, right? I don't know. I mean, it's an element of Zi, right? So I'm going to just call it Q like that, right? So maybe just so I get some more standard notation here. I mean, not standard, but so it looks sort of similar, right? That's the thing I'm trying to divide. That's the thing I'm dividing by, right? And so I get this, this up here, I get S equals Q times T, right? Plus R. Well, what is R going to be? R. R is just going to be, what? It's just going to be S minus QT, right? Like that. And then you have to prove some stuff. And what you prove here is this. So what is the thing we kind of use for a norm here? So on the space on Zi, right? We actually have this kind of norm. I mean, it's just okay, so let me write it in two ways. So A plus BI. So one way of writing it is just I write A squared plus B squared, right? So that's what it is, right? So it's that. But you could write it as also this, the length of A plus BI squared. And if we think about these, if we write Z instead of that, right? So this is like saying in Z, right, is the length of Z, the modulus of Z squared. But this is also the same as Z times Z bar, right? So that's a thing to keep in mind when doing complex numbers, right? And so we know, for example, stuff like this. We know that n of ZW. So let's take two things which are both Gaussian integers, right? We're computing their norm, right? Well, this is ZW. ZW bar, okay? But some math, right? So this is ZW, Z bar, W bar, right? And this is Z bar, W bar, right? And so this is NZ, NW, okay? So we're going to use this kind of argument all the time when dealing with these kind of spaces. And we have lots of like counter examples and examples of stuff using this kind of thing. So this is like a number theoretic norm here, right? And so it has the property that it's multiplicative in this sense. So the norm of the product is equal to the product of the norms, right? So that's a nice thing to have. Okay. And so it turns out here, right, that when I do this kind of division, so I had this S equals Q T plus R, right? And it turns out to be the case that NR is less than, I got to remember what it was. Something like 1 over. Oh, I'm going to have to cheat and look at my notes. So let me just. Oh yeah. Okay. So we actually get that NR, this thing is less than 1/2 of N of T. And this is somehow important when doing analysis with it, because remember, there's actually a square up here somewhere, right? When we do something, right? So we actually get that, which is nice. And so this gives a bunch of things. So Zi is a Euclidean domain and hence a PID. F X is a Euclidean domain and hence a PID. And we'll use these kind of examples quite a bit. And actually, I'm going to have to stop this lecture here because it's time to meet you guys.